Hello, everyone. I'm Li Ming from the University of Sydney. I feel privileged to talk about our work titled Semi-Online Multi-Machine with Restart Scheduling for Integrated Edge and Cloud Computing Systems on behalf of all authors. So first, I'll introduce about the background. Serverless computing at the edge provides lightweight, low latency, and ubiquitously available computing services. It provides functions inside sandboxes based on the runtime environments and deployed widely in mobile and IoT devices, including some computation-intensive applications such as machine learning and deep learning. It is vulnerable to overloading due to bursty arrival of computation tasks. So we are motivated to solve that problem. And a natural solution is to further offload this task to the remote public cloud computing infrastructure. However, using this way, there are some challenges. First, the delay caused by offloading is unpredictable. And second, it is impractical to maintain some copies of serverless containers running on the cloud due to the cost. So here, we surveyed some of the most popular tasks to be offloaded to the cloud for processing. The delay on the edge consists of pure processing delay only, while on the edge, there are additional delays, including uploading the task, loading the set of instructions used by the task, known as the loading delay. And from the figure, we notice that utilizing the cloud can significantly save the processing delay as for some tasks. But sometimes utilizing the cloud takes even longer than using the edge because of the additional uploading and loading delay. As a result, we need to schedule them wisely. So in this work, our objective is to design an efficient scheduler when a set of heterogeneous tasks overloads the edge nodes. Our aim is to minimize the overall make span of the task, that is the total time to finish all tasks. Due to the unpredictability as the cloud processing delays are demanded unknown, while the edge processing delay can be well estimated by the profiling techniques and are deemed known based on the stable performance of the edge nodes. This formulates a semi-online setting. However, the make-span minimization problem is challenging due to the fact that even in an offline setting where the processing time of all tasks on all processors are known, it is still NP hard. And the problem is further complicated by the fact that there could be multiple edge and cloud processors in the system, and they have unpredictable delays. So brief summary of our achievements. We propose the MRS with provable performance bound and the result to competitive ratio as a performance metric, which is defined as the worst case ratio over all problem instances between the make span output by the semi-online algorithm to the make span output by the optimal offline algorithm, where the processing delay of all tasks on all nodes are known as a prior. So we also implement a real-world system and achieve a substantial performance gain. So I'll introduce the MRS scheduling like algorithm design. So it is a approximation algorithm with a provable competitive ratio, and the restart means that if a task is processed as a cloud, we set a stop loss threshold for it. And if the processing time exceeds that stop loss threshold, the task is canceled and is left for the next round of processing. Yeah. So here we introduce the notations. We consider a system with M identical edge processors indexed by M and N identical remote cloud processors indexed by 1 to N. And we assume that m is larger than n or larger or equal to n throughout this paper, since edge nodes are lightweight devices and can be massively deployed, while the cloud nodes we have to rent it. And also, there are t independent and non-preemptive tasks indexed by I from 1 to t. And this is known to the algorithm as a prior, with the delay on edge processors AI being null. The delay on cloud processors BI is deemed unknown to the algorithm and the processors. Yeah. We also denote beta max, which is the maximum ratio between AI and BI, and T as the set of all tasks. So here, I will first introduce the high-level design guideline of MLS. So at the beginning, since we only know AI values, the edge processor should start work on the task with smaller AI values, and the cloud processor should start to work on the task with larger AI values, so that a task with large AI but probably small BI can be completed faster as a cloud. However, it is possible that a task with large AI has a much larger BI, so it is not worthwhile to process it at the cloud. Unfortunately, BI is not known if the task is not completed. Therefore, we are motivated to set a stop-loss time duration for it. The stop-loss duration is set to AI at the beginning, and if the cloud processor has exceeded the stop-loss, it will cancel processing these tasks, so give it opportunity to handle other tasks, probably with smaller BI. And we design it in terms of rounds. The step 1 to 4 is repeated until all tasks are completed. So first, we sort the task by their AI values, and the edge processor starts from the head, while the cloud starts from the tail. And if a task processed on the cloud has exceeded the stop-loss threshold, it will be canceled. And when all tasks have been tried once, if there exists unprocessed tasks, we need to reprocess them. For the case round, we increase the stop-loss time duration to k plus 1 times AI. So for the second round, the duration is larger than the first round. So right. And here is a figure which an example with 3 rounds. So the green ones are tasks completed locally on the edge, and the yellow ones are tasks completed on the cloud. The green ones are timed out on the cloud and left to the next round of processing. So note that in the last step of each round, the cloud processor must increase its stop-loss time duration. This is because the task have already been tried once by a cloud processor, and we have known that the BI is greater than k times AI. Therefore, we increase the stop-loss time duration to k plus 1 AI. And also, please note that canceling tasks on the cloud might seem wasteful in some cases, that the task is restarted on the cloud and again. However, first, this situation does not happen very often. And second, in many other cases, it is actually saves much time, as the edge processor will complete them in the next round to avoid significant time wastage on the cloud. The benefits overweights the drawback, and thus the overall performance is improved and bounded. So the detailed algorithm design can be viewed on our paper, and here we analyze the competitive ratio of the MRS, and I'll briefly introduce the proof, but the detailed proof can be viewed on the paper. So first, we have the MRS basic property, which is at least one of the last tasks in round K is completed by an edge node. So this can be proven by contradiction. Suppose that all last tasks in round K are completed by closed processors. Let tau denote the completion time of the last task, which is here, tau. And for any edge processor J, its last process task in round K is completed before tau, say that at this time. And as a consequence, the edge processor J does not process any tasks in this time duration. However, this is contradictory to the design of the MRS algorithm, where the edge processor kills the task being processed as a cloud and processed in round K, even if its state is cloud. So even if it's processing in the cloud and edge processor becomes idle, it kills the tasks. And so yeah, this property is proven by contradiction. And right, then we have the second lemma, which is the max span of MRS is no larger than the max span of benchmark scheme B. Benchmark scheme B is we utilize all M edge nodes, but leave all the cloud nodes idle. So we use edge nodes only for benchmark scheme B. And the benchmark scheme B is like if we use edge nodes only, it is like going to take longer time than those completed on the cloud, because MRS at least it schedules some tasks on the cloud, and it's very straightforward. We can prove that according to the properties. As for lemma 3, we have the property of non-overlapping subsets of tasks, and it is actually pretty much straightforward from the figure. So device 1, 2, 3, they have their own schedules. And if we sum them together, it is actually less or equal to with some like 3 times the duration of device 3. So yeah, basically you have the sum of all the like actual time on the device is smaller than the number of devices times the maximum duration on the edge devices. Yeah. So here is like a sketch of our whole proof. So we use lemma 3 to derive an like a relationship between AI and C star max. So the C star max here is the optimal schedule. And from lemma 3, we derive a relationship between AI and C star max. From lemma 1, we further prove that the make span using only edge processor but not cloud processor, which is the CB max, and is smaller or equal to this value and this ratio times C star max. And from lemma 2, we further prove the relationship between CM max, which is like the make span under our MRS scheme, and like the make span under the scheme B, which is CB max. So we can conclude that theorem 1, so CM max is smaller or equal to this ratio times C star max. So that's the relationship between our make span, CM max, and the optimal make span if we know like everything. That's C star max. So also we derive the beta max, and we can conclude that MRS achieve a competitive ratio of this, which is 0.1. Cool. So we also design a system to implement the MRS. So as for the system, we have the main controller, which schedules the whole thing, and also the edge scheduler, MS. We run the MRSE on the edge scheduler, and also the cloud scheduler with a timer, which receives the kill signal, and like if timeout, the timer simply kills the processing on the cloud processor, and the MRSC is implemented on the cloud scheduler. So we implement the experiment system with 5 identical edge nodes and 2 identical cloud nodes using virtual machine technology. So they all run Ubuntu. So for consistency. And we implement different task sets, which includes different short video. There are tasks to be processed by different models. And we implement each task as a short video inference task using deep neural network. We implement 7 different task sets denoted T0, T1, all the way to T6, and 6 different DNN models. So as we analyze one group of tasks, the one task set, which is T0. And in the first figures, we use list, Shmoy, LPT, which is like longest processing time first, and short SPT for shortest processing time first as the benchmark schemes. And it is shown that using list, the processing delay is larger than 300, similar for Shmoy. For LPT, it's around 200, actually a little bit more than 200, I suppose. And SPT is around 230. As for hours, we only, like MRS schemes, we can achieve like 180 seconds processing delay. And as for like task 16 and 19, we notice that even they are scheduled on the cloud twice, the performance is still better than the other algorithms, which continue to finish processing them on the cloud. So this task may have very long processing delay on the cloud due to uploading and loading. And also we demonstrate the results of other like task sets, T1 to T6 here. It is shown that in all cases, MRS outperforms other schemes, and on average, MRS outputs the best existing scheme by 17%. We also do a simulation to simulate a large-scale system because, like, in our experiments, we only have 5 edge nodes and 2 cloud nodes. But in the simulation, we can have more than that. In this particular simulation, the total number of tasks being processed is set to 1,500, and the number of edge nodes is set to m equals 36, and the number of cloud nodes is set to n equals 6. So we implement this simulation in Python and also run it like on Ubuntu. And the results are shown in the figure. So similarly, in all cases, MLS outperforms all existing schemes and achieves a performance gain of around like 25%. So as a conclusion, we propose a novel algorithm named multi-machine with restart scheduling, in shorthand MRS, for integrated edge and cloud computing system with a provable performance bound. And the restart mechanism avoids the processing delay as the cloud being excessively large, which result to the competitive ratio as a performance metric and derive an O1 competitive ratio. That's all of my presentation. Thank you for listening.